So today we are going to see now the energy stored in a magnetic field. Okay. Now we have seen that when you put the key, this key in the circuit over here, this key in the circuit, the current will flow through the battery, through the inductor. So I'm just considering that I am trying to put some charges, or I'm trying to pass charges through the inductor, right? So as soon as you put the key, the current does not go to a value, a steady value, say I naught directly. It slowly increases as shown in this graph over here. Okay, you can see in this graph that the current value is slowly going to increase, then become steady after some time, and if I remove the key, then it will decrease in this way, right? Okay, so now whenever the current is increasing, as I put the key, there is going to be a change in current. If there is a change in current, there is a change in magnetic field. If there is a change in magnetic field, EMF is going to be induced. And what is the direction of the EMF, or how is this EMF? It is trying to oppose the change in the magnetic field. So we have to spend some energy in maintaining some steady current I naught to flow through this circuit. Okay, I have to perform, or I have to spend some energy in establishing a continuous steady current I naught in this circuit, right? Now let's see what is this energy that is spent and where is it stored in the inductor. Where is this energy stored in the inductor? Okay, so we had seen the expression induced EMF E is equal to minus L di by dt. I have to take a charge dq through this circuit, right? So work done in moving charge dq against this EMF. The work done in moving the charge dq, EMF is going to oppose the motion of dq. It is trying to oppose the increase in current, right? So I have to do some work against this EMF. So I get the expression dw is equal to E minus E into dq, right? Okay, so from where did I get this? You will remember the equation V is equal to W upon Q. So I can say W is equal to V into Q, right? So V is nothing but the potential difference, or EMF. I can substitute this as E. So work done is EMF into the charge. Now minus sign is just indicating that we are performing the work against the EMF, right? And what was this E? From here I get E is equal to minus L di by dt. Okay, so rearranging the terms, I have L di dq by dt. dq by dt is nothing but the current. This dq by dt is nothing but I. So I have dw, the small work done to move small charge dq through the circuit, is L di into I. I am not interested in the small work done. I want the total work done in establishing a steady current I naught. So I want to increase the current from 0 to I naught. So I'll use the integration. The total work done W can be written as integration of dw. All this small work done, I'm going to integrate it. From where to where? Initially the current was 0. I'm going to take it to I naught. So from 0 to I naught असा करंट वाढवलाय. आणि dw काय होतं? dw चं जी काय व्हॅल्यू होती, this terms I'll put it over here. So I have L di into I, right? So L is again a constant. It is not depending on anything. That is the self inductance of the inductor. I can take it out of integration sign and I get something like this. L comes out, integration 0 to I naught, I into di. How to solve this integration? You know this formula. Integration of x to the power of n dx is equal to x to the power of n plus 1 upon n plus 1 between the limits a to b. So from there I get this equation. W is equal to half L I naught square. Now this work done in moving the charge is nothing but stored as the energy. Okay, it is just stored as the energy. So this energy is called as the energy stored in the magnetic field. Where is this energy going to be stored? It will be stored in the magnetic field, right? So energy stored in the magnetic field is given by half Li square. It is half Li square. From that, I can find the energy stored in the magnetic field per unit volume also. Okay, that we will see later. Anyways, so I get W is equal to half Li naught square. That is the energy stored in the magnetic field. Okay, now we had said that we will see one definition from this, right? So using this W is equal to half L I naught square, I'm going to make one definition, assuming that if I naught is equal to 1 ampere, then what will W be? Then W will be L by 2. I can say that L is equal to W by 2. For 1 ampere current, L, the inductance, is equal to twice the work done. Okay, so from this I can make a definition for self-inductance, that is, self-inductance is numerically equal to twice the work done in establishing magnetic flux associated with unit current in the circuit. I repeat, self-inductance is numerically equal to twice the work done in establishing magnetic flux associated with unit current in the circuit. Also, you can see that we have got an equation for the energy in the magnetic field, energy stored in magnetic field, as half L I square, where L is the self-inductance and I is the current. If I compare it with the kinetic energy, that is half mv square. Okay, by comparing these two equations, I can say that this L can be compared to m, and that is how it is. Okay, that is how it is. This L is also called as electrical inertia. Why? Because it does not want any change. If current is increasing, it doesn't want it to increase. If current is decreasing, it doesn't want the current to decrease. So it is similar to this m, which is nothing but the mass or inertia in motion, right? So L, inductance, is nothing but called as the electrical inertia. It opposes any sort of change in the magnetic flux or any change in the current in the circuit. Thank you.